Hi students. In our earlier discussion, we were about to start our Maxwell Boltzmann statistics. So we discussed this slide in detail. So this statistics applies to the particles which are identical, distinguishable, without spin, and the example of such system is molecules of a gas. And we are going to see how Maxwell-Boltzmann statistics applies and what are we going to study using this statistics. So we also saw how to divide the system into cells and the further quantum states, etc. And now we are about to proceed here in the next slide. So where if I take a system, I'm going to consider N1, N2, Ni particles distributed in a state of energy E1, E2, Ei, etc., Ei respectively, such that the N1 particles have E1 energy and so on. So the total number of particles in a system is given by capital N, which is equivalent to N1 plus N2 plus N3, so on till Nk, where I goes to 1, 2, 3, etc. till it's a huge number, it's a finite number, and the total energy of the system is given by U equal to N1 into E1. Here you have to understand words. Say, for an example, if I have 10,000 molecules, I can have 2,000 with the same energy range. I can have 3,000 molecules the same energy range, and so on. So if I want to calculate the total energy, I had to product the even energy of N1 particles plus E2 energy of N2 particles, and so on, so that I get the total energy of the system. So since the entire system is isolated, the total energy of the system is constant. Now we have to understand what is statistical equilibrium. So I said the energy of the system is constant. So now what happens inside a gas system? The molecules of the gas have a movement inside the cylinder, inside the container, and these molecules tries to collide with each other or collide with the walls of the container and loses its energy. In a sense, the energies are transferred from one particle to the other particle. So we said in the initial itself, we said that the energy of the system is constant, it is not going to change. But here we understand that there is only a transfer of energy from one molecule to the other, meaning the number of molecules changes from one energy band to the other energy band, but the total energy does not changes. So when this collision or when this movement keeps on happening between the molecules, these N1, N2 particles changes continuously, and it tries to try to set itself in a particular microscopic state, and it keeps on shuffling, and there is a particular most favored distribution when all these molecules settles down, and after that there will not be any type of distribution, and this favored distribution or the favored settlement of all these molecules in a particular energy states are called as statistical equilibrium. So once a system attains this statistical equilibrium, then we take this system for understanding the distribution of energy using various statistical methodologies depending on the particle's nature. So here it is Maxwell's Boltzmann energy distribution. So how to proceed with it. So as I have given in the earlier slide, the total number of particles in a system is given by this equation, n equal to n1, n2, etc. So just taking a differentiation of above equation, that is a small change in the number of particle dn will obviously be 0, because we know that the total number of particles in the overall system is constant. Similarly, we have this equation total energy of the system U equal to N1 E1 plus N2 E2 etc. And when we take a differentiation of the energy, it again goes to 0, because we know energy is constant as the system is isolated. Now, in equilibrium state, actually, as I explained to you, the statistical equilibrium, the distribution of particles among various quantum states has a maximum probability of occurrence, because we know that the system lies in, the system always tries to tends to equilibrium, even if you change it from its original position. The nature always tries to tend the system to equilibrium. So when this equilibrium, statistical equilibrium is attained, that is the maximum probability of occurrence of this particles in a particular energy states. So now I am going to give two colors for these equations, an yellow star and a red star, because I am going to use these two equations in my further slides for discussion. So these are the energy states. So E1 energy states have N1 particles, E2 have N2 particles, so on. So now I am going on to distribute the particles now. There are total of N particles, yes. The number of ways of choosing the first particle is n ways, correct? Yes. Now I have already placed my n particle. Now I have with me only n minus 1 ways. So the number of ways of choosing the second particle is n minus 1 ways, and it goes on. So the number of ways of choosing the third particle is n minus 2 ways. So you can see I have colored it. So third particle is n minus 2 ways, and the number of ways of choosing the n1 particle is n1 minus 1 ways. So when I write it in a general form, so the total number of ways of choosing the n1 particle is nothing but n into n minus 1 into n minus 2 and so on till n minus n1 plus 1. This minus sign goes inside, so it becomes n1 plus 1 number of ways of choosing n1 particle. So again I have written the same thing in the next slide. So now how can you write this? So if you just give an example for this, and if you just work it out, you can write this as n into n minus 1 into n minus 2 so on into n minus n1 factorial divided by n minus n1 factorial. So which can be written in a compact form as n factorial divided by n minus n1 factorial. So the n1 particles are distributed in the first energy level. So as I said before, I have total of capital N particles with me. Out of that, a bunch of n1 particles I have taken, I have distributed it in the first energy level. Now, what will be the remaining particles I have with me? It will be n minus n1 particles. Now, I am going to distribute that in the second energy level. So, the total number of ways of choosing the n1 particles in the first energy level is given by x1 equal to n factorial divided by n1 factorial into n minus n1 factorial, which is equals to nc n1. This is exactly the way we have written our thermodynamic probability in one of our earlier slides. So now, yes, I have finished the total number of ways of choosing n1 particles. So while this n1 factorial comes here is to just have the meaningful ways, meaning if there are any repetitions, these will be taken care by writing this n1 factorial. So now the total number of ways of choosing the n minus 1 particles in the second energy level is then given by x2 equal to n minus n1 factorial by n2 factorial into n minus n1 minus n2 factorial, which can be written in a compact form as n minus n1 c n2. And if it goes on, I can generalize it by writing xk equal to n minus n1 minus n2 till n of k minus 1 c nk. Well, you can make a note here. So whatever you have here n1, you will have here n1. So if you have n1 here, it is n2 here. So that is the reason you have k minus 1 here. So it is here. You have your nk. So this is a generalized form of writing it. Now the total number of distinct ways of obtaining the distribution of particles among all the energy levels is given by just the product of all the ways, that is x is equals to x1 into x2 into x3 and so on. So which can be written as n factorial divided by n1 factorial, n2 factorial, n3 factorial, so on till nk factorial. Okay, now we also discussed that there are still more quantum states Gi in every energy levels. So that can be shown like this. So this n1 particles are not only in the same line, and it also have some quantum states to be distributed like this. So here G1, G2, Gi are the quantum states. Now we are going to see how are we going to arrange all these n particles in Ni ways and Gi ways. So there is no restriction there is no restrictions for the number of particles to be occupied in quantum states. So that is direct. You have Gi power Ni ways of arranging Ni particle in Gi states. So keeping all this in mind, considering all the quantum states belonging to all the energy levels, the total ways of arranging all the particles is then given by W equal to n factorial. So this is what the number of ways you arranged n1 particles in the first energy level, second energy level, third energy level, etc. And these are the ways in which you have arranged all n1, n2 particles in G1, G2 quantum states, etc. So this is the total probability. So now how can you write this expression? So W equal to n factorial, you instead of summation, you have pi here, which represents product of the quantities. It is not summation as you usually use. This represents product of the quantities. So you could see here the product of Gi Ni is written as Gi Ni here, and the product of n1 factorial, n2 factorial, etc. is written as Ni factorial, and this is equation number 1, where pi represents product of the quantities. Okay, we will discuss the rest of the calculations in the next class. Thank you.